In this week's video, we're going to be taking a look at how to correctly store a user's password in a database. So we're going to cover the concept of hashing, salt, rainbow tables, and then finally we're going to be taking a look at a library called bcryptjs within Node to see how to exactly use it in order to actually go ahead and store our users' passwords in a database correctly. So there's quite a lot to cover, so let's get into it. So the first thing that we need to establish is we under no circumstance can ever store a user's password in plain text in our database. So what does plain text mean? Well, very simply, what plain text is essentially, let's imagine you have your sort of sign up form where you might be prompting the user for their sort of username and then their password, right? Now, if you go ahead and take the password exactly as it was entered and then store that in the database, that is called storing the password in plain text, and that's a sort of big no-no. That's something that under no circumstances should you ever do. Let's say someone who's not supposed to actually have access to your database does in fact get access to your database. Well, now what's going to be happening is all the passwords that you have stored in your database are going to be vulnerable and going to be compromised because they now have fallen into the wrong hands, and they're just open in plain text. They're just easily readable. They're just right there, and you can just go and use them. Now, the reason why this is especially important to kind of make sure that this never happens is because what ends up happening is, despite the fact that users should never do this, many users are still very guilty of doing this, and that is that they use the sort of same password across multiple different applications. And so what that means is that they can, of course, be storing a password in your database that is the sort of exact same password that they use to log into their bank account or into their email. So storing passwords in plain text is a giant no-no. We never, ever want to make that happen. So the sort of question is, if I can't store the password in plain text, how do I store a user's password in the database? So one of the approaches that you might consider is to sort of take the password that you kind of got out of the form, out of the sign-up form, and of course, instead of storing it in plain text like we just discussed you should never do, you might go ahead and encrypt that password and then take the sort of resulting encrypted password and then store that in the database. Now, this is actually a pretty decent thought. This is certainly going to be miles better than actually storing it in plain text, but this is still not going to be the optimal solution. And the reason why this is not the optimal solution is because, as it turns out, something that can be encrypted can of course be decrypted, as so long as you know what the key was used to actually go ahead and encrypt it. So some kind of key was of course used to kind of lock this value away to kind of encrypt it. If you get a hold of that sort of same key that was used to lock it away, you can then of course just use it to unlock it, which means that if now we kind of come back to the sort of same scenario where your database kind of falls into the wrong hands. So true, now all the passwords that are stored within your database are not going to be the sort of plain text version. It's actually going to sort of be the actual encrypted version. But now, should this hacker for any reason kind of get a hold of the actual key that was used to lock these passwords, well, now once they have the key, all of those passwords are now once again just as good as plain text, because they can just go ahead and unlock all those passwords and then just go ahead and read it right out. So clearly we know that we can't store it in plain text. We know that we can't store the encrypted version of that, because that's, once the key is sort of compromised, just as good as plain text. Well, then that leaves us with what? Well, the answer, of course, is that leaves us with hashing. So let's first establish a couple of sort of baseline facts about what hashing is, and then we're going to kind of work our way up to see why this is sort of the optimal solution. So one thing that we need to know about hashing is that the sort of same input always produces the sort of same resulting output. So essentially what's going to end up happening is, if let's say you kind of take the word password, which was what the user entered within your sort of sign-up form, you take that word password, you run through your sort of hashing algorithm, you're going to get some kind of jarbled mess out on the other end of this sort of hashing algorithm. But the cool thing is, every single time that you're going to go ahead and take the sort of same input, the sort of same word password, pass it through the hashing algorithm, the result that you get on the other side is always going to be exactly the same. So another very important thing about hashing algorithms is the fact that once you've actually taken a certain input and you've run it through your hashing algorithm and you got the sort of resulting jarbled output, which we're now going to be referring to as the hash, once you have that hash, there's no way to kind of work your way back from the hash to the original input. Which means, unlike with the encryption, when you actually have something that was encrypted, you could of course go ahead and decrypt it and then work your way back to the original value. With hashing, that cannot be done. Once you have a hash, there's no way to kind of go back from the hash back to the original input. So now we can start to see that maybe hashing might be the actual optimal solution of how to actually go ahead and take our users' passwords and store them in a database. And if that's what you were thinking, you'd of course be right. Hashing is the correct way to go ahead and take a password and store it in the database. And the flow would basically be a little something like this. You have your sign-up form. You'll then take the actual sort of entered password that the user kind of entered within this particular form, run it through your hashing algorithm, then that resulting hash is now where you're going to go ahead and add within the actual database. So now if you're kind of thinking about what might happen if the sort of hacker gets a hold of your database, well, now they have kind of no way of kind of working back to what the original passwords were, because they're not in plain text, they're not encrypted, which means that there's no key to kind of go ahead and unlock it. All they're kind of left with right now is going to be a hash. So they just have a table full of usernames and then just a bunch of jarbled hashes. There's no way to actually know what the original password was, which is why storing a hash in the database for the password is going to be the sort of optimal solution. But this itself is not enough. See, the problem of course is, while it's true that the sort of actual individual hash cannot be reversed, what the hacker might actually be able to do is kind of guess your password. So basically what they might do is they might actually build their own little script that might run through sort of millions upon different possible permutations of what your password might be, AAB, AABCC, and then, you know, actually working their way up to actual individual words like the word password, the words 123, password 123, and whatever you kind of want, all different types of, you know, potential password combinations that you might have thought of. They have already thought of them as well, and they in fact have lists upon lists upon lists of potential passwords. And now what they can do is they can actually take the resulting hash to check to see if that resulting hash exists within your database. And if it does, well, now they know what the sort of corresponding password was that created that hash that you now have in your database. So while they actually have no way of taking the individual hash and working their way back to what the original password was, but they can in fact take a bunch of permutations and then guess what the password might be, because if they find the resulting match from their hash that they just produced to a hash that was stored in your database, they know which word it was that created this hash that you have stored in your database, thereby cracking the password. So because of exactly this problem, one of the things we of course want to make sure when we actually choose the right hashing algorithm for our application, and this is going to be unlike all other instances of computer science where we typically try to use a sort of algorithm that runs very fast, but when we choose a hashing algorithm, we actually want to make sure that it's going to be a very slow algorithm. And this is exactly the reason why. Because if it takes you, you know, 2 to 4 seconds to go ahead and produce a hash, well, of course, that now makes the sort of guessing attack vector that a sort of hacker might have very impractical. Because if they have to run through millions upon millions upon millions of different permutations just to kind of guess to see if a resulting hash is going to live within your database, if each one of those hashes takes upwards of a second or 2 or 3 seconds to actually go ahead and produce, of course, running through that many different permutations is going to become wildly impractical, thereby making your actual passwords that you have stored in your database pretty secure. But once again, we're not out of the woods just yet. See, because there's this thing called rainbow tables. Essentially, what a rainbow table is, it's just going to be a sort of giant table that has a list of a bunch of really common passwords and their sort of resulting hashes already pre-computed for you. Basically, what that means is now the fact that you actually chose a slow running algorithm to produce your hashes is of course not going to be useful to you, because right now the hacker doesn't have to produce a hash and then check the sort of resulting hash against your database. They already have a table full of a bunch of pre-computed hashes with their sort of corresponding passwords. So now instead of the hacker producing the hash, all they need to do is take their existing hashes that they already have within their table and then scan your table to see if they actually have a match. And if they do, well, they already know exactly which password it was that created that hash without them actually having to go ahead and produce the hash. So the fact that you chose a slow algorithm is going to be absolutely useless to you. And so finally, that's where the concept of salt comes into play. So in order to understand what salt is and how it works and how it actually sort of stops this actual attack vector of using the rainbow table, let's actually take a look at some code examples of me using a library called bcryptjs in a sort of Node application to see exactly how we hash passwords, how salt actually works, and how we actually stop the sort of rainbow table attack. So let's take a look. Okay, so here, as you can see on screen, what I have right now is a simple Node application, and all I've done right now is I've went ahead and I've required the bcryptjs library, which I've installed using yarn. You could of course use npm. It's just going to be bcryptjs. And then what I'm going to be doing is I'm going to be calling this bcrypt get gen salt function 4 times. Now 4 times is nowhere near enough to really highlight the point that I'm really trying to make. We would have to really do this way more times, but this at least gives us a slight window into the sort of concept I'm trying to make right now. And that is that what we're going to do is we're going to go ahead and generate this salt that I keep referring to, and the salt is going to be unique every single time. It means all 4 of these sort of calls to generate salt will be producing an actual different salt. So let me show you first of all what the salt is, and let's also see how the salt actually looks different from each individual instance. So now in my terminal, if I actually go ahead and run node app.js, we can see that we have the sort of resulting output. We have all these 4 salts. So immediately the first thing we can see is what the salt actually is. And it's pretty much just going to be a random, completely random generated string that's going to be generated for us by Bcrypt. And one thing that's also important to note is that each one of these strings are going to be completely unique. Now, like I said, 4 is not really going to be enough of a sort of sample size to see truly how unique they always are. But the basic idea of what a salt is it's going to be a random string that is always unique every single time that you call it. And so now, how does this actually help us? Well, as it turns out, when you actually take a password or take any kind of word and you run it kind of through a hashing algorithm, if you make just one seemingly very small change, the resulting hash is going to be vastly different. So for example, let's imagine we just have the word password, P-A-S-S-W-O-R-D. If let's say you now take that same exact word, but leave off one of the S's and then run it through the sort of hashing algorithm, the sort of resulting hash is going to be completely different, even though it's only off by 1 letter. So now, since the whole point of the rainbow table is that we have a list of a bunch of pre-computed hashes with the sort of corresponding passwords, this only works on the assumption that the password that we have stored in the database is a sort of already known password that has already been used in the past. For instance, the actual word password. But the thing is, if we actually use a salt, that's no longer going to be true. So essentially, the way that the salt works is going to be like this. We're going to have the sort of sign-up form where the user is going to go ahead and enter their username and then their password. We're going to take the password out of that form, and then to the actual password that they have given us, we're going to go ahead and generate one of these salts that Bcrypt gives us, and then we're going to take the salt plus the password that's given to us by the user, concatenate the two, and then run the hash over that. Which now what that means is the actual resulting hash is going to be completely unique, and it's going to be unique for every single user, even if we end up having two users in our application using the exact same password, because the salt is always unique. And the cool thing is, this now renders the entire sort of rainbow table useless, because the whole point of the rainbow table, as I mentioned before, is it pretty much works on the assumption that we're going to be working with sort of pre-existing passwords or sort of known passwords. But if we take the salt and append it to this known password, we're basically making the sort of resulting hash a completely unique hash, because the salt is completely unique and completely random, and it's going to be unique for each individual user, and that's going to be across the board, which means that this rainbow table now no longer will have the password that we have here, because how could it possibly know what it is? It's unique, it's totally random, which means that now by actually having this sort of salt attached to the password, we essentially reduced our hacker back to their first attack vector, and that is to actually go ahead and guess what the password might be, as opposed to being able to sort of use the pre-computed passwords, because the pre-computed passwords are now useless because they don't account for the salt. The salt is completely unique and completely random. Now, since they have to go back and actually guess passwords, the fact that we've chosen something like Bcrypt, which is a very slow running algorithm, is of course going to make our passwords, the way that we stored in the database, very secure, because they don't have the pre-computed ones. They have to guess, but guessing something that takes upwards of a second or two to kind of guess each individual one, and they have millions of permutations to run through. Of course, in this case, it becomes extremely impractical for them to be able to crack the passwords within our database. So now, with all of that sort of theory out of the way, let's actually take a look at how Bcrypt actually works. Okay, so as you can see on screen, what I'm doing right now is I'm going to go ahead and call the sort of gen salt argument, which you've already seen. This goes ahead and produces that random string, the sort of salt that we're going to be appending to the password. But the thing is, we're not the ones that are actually going to be appending this to the password. Bcrypt is going to be doing that for us. So what we're going to now do is we're going to go ahead and call the Bcrypt hash method. The first argument that you pass into this hash method is going to be the actual password that you're trying to hash. So in this case, that would basically be what you're actually getting from the user from the sort of sign-up form. That's what you're going to be passing in as the first argument. The second argument is then going to be the salt that was just generated for us. And then the result of that is going to be the sort of actual hash that was produced by actually taking the sort of salt plus the password, concatenating the two, and then running the hash algorithm over that. That's now going to be our resulting hash. So let's run this code and actually see what we get in the output. So as you can see, we kind of get this massive jarbled mess. This is, of course, not reversible. You can't go from this back to the original password, and this is now what you would presumably go ahead and store in the database in your user's record under the password column. Now, just to kind of illustrate the point again of how the salt makes each individual password unique, let's go ahead and run this exact same bit of code again. Right? So we're going to be running it twice within the same file using the exact same password, but because the salt is going to be different, the resulting hash is of course going to be different as well. So let's actually see that in action. Okay, so here I am. I've just pretty much copy and pasted the sort of same bit of code. So these two things are doing exactly the same thing. We're calling the same gen salt. We're using the exact same password, just a string password. But now as I run this, let's see, we're going to get two resulting hashes. And you can see over here, this one ends with key, with the word key, and this one over here is ending with the sort of YK0. So far we've seen how the actual salt will stop against the rainbow attack, and how hashing and using Bcrypt, which is a very slow algorithm, is a very nice and safe, secure way to store passwords in a database. But I'm sure you have this sort of burning question in your mind right now. If the password that we're storing in the database is not the same password that the user entered, but it's going to be the sort of jarbled mess that we get out of the hashing algorithm, and it cannot be reversed, how do we log a user in? Right? Because now if the user goes to the login form, gives us their password that they had used when they signed up, if this is not the password we have stored in the database, how do we compare the two, right? Because presumably what you'd want to do is you'd want to take the password that they just gave you in the login form, compare that against the password that we have stored for them within the database, and if those two match, of course they're going to be logged in. But in this case, they're not going to match, because what we have is a hashed password, and what they've given us is going to be the original password that they use, which of course we never saved in the database. So how do we actually log a user in to our application, given the fact that the password that is stored is of course hashed and not the original password? As it turns out, there's actually a compare method that Bcrypt offers, and it works just like this. Okay, so as you can see here on screen, what I'm now doing is I'm actually calling the compare method that Bcrypt offers. The first argument that you pass into the compare method is going to be the actual password you're trying to compare against, which means in this case, it'll be the one that you're pulling out of the actual login form that the user has given you in the login form. And then the second argument is going to be the actual hash password that you stored in the database for this particular user. And then what you then get is going to be the sort of resulting argument that's going to be a Boolean of either true or false of whether or not these two individual arguments or these two passwords actually match. And what Bcrypt is actually going to do now is it's going to take the sort of password that the user gave you now during the login phase. It's going to run the sort of hashing algorithm over that input, and then it's going to go ahead and compare the two underlying hashes. right? So essentially, you're right. What we actually have stored in a database is going to be the actual hash. What the user has, of course, given us as not the hash is, of course, just going to be their original password. So what we're going to do is we're going to take the sort of same hashing algorithm that we ran over the original password and now run it over the password they've just given us. And since the same input always results in the exact same output, whenever using a hashing algorithm, the same input always gives you the same output. If the password is, of course, going to be the same as they've given us during the sign-up phase, the resulting hashes are going to be the same, and then we can, of course, log them in if they match. But if it doesn't match, we know that the password that they've given us is not going to be the same. But I know you're probably still confused, and for good reason. I just told you about a minute ago that the password that we save in a database, the sort of hash, is a sort of result of the fact that we've taken the sort of original password that the user has given us, plus the salt, we concatenated the two, and then we produced a hash out of that. But when the user is giving us the password during the login phase, they're only giving us their actual password. They're not giving us the salt. So if we don't actually have the salt, the hashes are not going to match because we're not running the hash over the same input. It turns out Bcrypt handles that for us as well, so let me show you. So now what I'm doing here is I'm pretty much going to go ahead and log the salt that we got from the generated salt. We're then going to go ahead and log the hash that we get from actually calling the hash method. And now let me show you something very interesting. So as you can see, this is the actual salt that was generated for us right over here. And then over here, you can actually see this is the actual hash that was generated for us. Now, if you actually look at the sort of first part of the hash, you'll notice that it looks pretty much exactly the same as a salt. And that's because it actually is. So it turns out what Bcrypt does is pretty much going to be doing two things. First of all, it's going to take the sort of password that you've given it, plus a salt, concatenate the two, produce a hash out of that. So now we have the hash right over here. Then it's going to take the exact same salt that it has just generated and then go ahead and concatenate that into the hash. And then that's what we now go ahead and store it within a database. So now when you actually go ahead and call the compare method, you actually give it the hash that you have stored in a database. So in this hash actually lies the salt. So what Bcrypt is now going to do is going to pull the salt out of that hash, take the password that was given to you from the login form, concatenate those two, run the hash over that, and now those two hashes, when they compared, are either going to match or not going to match. But if the user did in fact give you the correct password, we're going to have a perfect match because we're using the exact same salt plus the exact same password. Now finally, one more thing I want to just quickly point out about Bcrypt is that when you actually call the generate salt function, it actually can accept a sort of optional argument. So this argument is basically going to be called salt rounds, and all salt rounds really does is it sort of dictates the sort of cost factor of how expensive or how long will it take to kind of run this operation. So by default, generate salt, which is pretty much by default use 10. That's just the kind of number that it is. The higher that number is, the sort of higher the cost factor is. So it is recommended, based on some of the forums that I've seen, that right now it's recommended because of how powerful computers are, you want to kind of use the number 12. But the basic idea here is you want to try to find the sort of sweet spot, because the bigger this number is, the sort of more secure your actual algorithm is going to be, because the longer it's going to kind of take for your hacker to run through the guesses. But at the same time, you have to remember that you're going to be using the sort of same algorithm to kind of, create an account and then of course log in your users when they're trying to actually log in. You're going to be using that sort of same hashing algorithm. So this sort of cost factor is a bit of a double-edged sword, because while it's true that it'll actually make the guessing process for your hacker a lot longer, but it also means that your users are also going to have to wait a little bit longer to actually log in. So the trick is to kind of try to find that sweet spot where it's just long enough to kind of make it impractical for your hacker to try to hack all of your passwords, but also not so long that your users are going to lose patience when they're trying to log in. Well, anyways, that does it for this video. Hope you enjoyed it. I hope you found it useful. If you did, please drop a like, subscribe, and I'll see you next week in another video. Woo!